This paper introduces EventEgo3D, the first approach for 3D human pose estimation from an egocentric monocular event stream. The increasing adoption of head-mounted devices for augmented reality and virtual reality applications necessitates precise 3D human body pose estimation of the user to enhance immersive experiences. Egocentric 3D body pose estimation involves estimating the 3D body pose of the user from the perspective of the head-mounted device, also known as the egocentric view. While numerous works have performed 3D body pose estimation from egocentric views, the robustness of current methods in scenarios involving fast motions and low-light conditions remains a significant challenge. The primary factor contributing to this limitation is the reliance on RGB sensors in traditional approaches. The utilization of head-mounted devices with RGB sensors in environments with low lighting conditions and fast-paced motions often leads to unreliable 3D body pose estimations, a critical requirement in numerous applications. Event cameras record streams of asynchronous per-pixel intensity changes called events. This enables high dynamic range, lack of motion blur, low latency, improved data bandwidth, and less power consumption. Moreover, event cameras generate no events in scenarios with no observable motion. Event cameras can capture motions with high temporal resolution and operate effectively in low-light scenarios, outperforming traditional RGB cameras. This enables event cameras to provide high pose update rates and maintain robustness in challenging low lighting conditions. Our work focuses on predicting the 3D human pose through the egocentric perspective using event streams. We design a head-mounted device with an attached monocular event camera with a fisheye lens providing a 190-degree field of view. Also, we synthesize and record synthetic and real datasets to enable training and evaluation of EventEgo3D. The proposed approach, EE3D, takes a monocular egocentric event stream as input captured by the user's head-mounted device and estimates the 3D pose of the subject. Our synthetic dataset is generated by rendering synthetic videos of human motions from an egocentric virtual camera at a high frame rate, which are then fed into an event stream simulator to produce event streams. The human body masks are obtained by projecting the 3D human body shape onto the egocentric virtual camera. We use a markerless multi-view motion capture system to acquire a real-world dataset with egocentric event streams and the corresponding ground truth annotations. The annotations include 3D poses of the subject and the corresponding SMPL body fittings. Simultaneously, we use a head-mounted device to record the event streams and track their 3D position in each frame through multi-view images in the world coordinate frame. The global 3D poses and SMPL body shapes are projected into the local coordinate system of our head-mounted device. Additionally, the human body masks are obtained through the 2D projection of the SMPL shapes. Our framework takes a monocular event stream as input and estimates the 3D human body pose. To process the event stream effectively, we convert the 1D event stream into LNES frames. We employ a two-step approach for pose estimation. First, 2D body joint heat maps are generated using an encoder-decoder network from the input frames. Then, a lifting network is utilized to convert the heat maps into 3D body joint estimates. We implement a frame buffer that retains the event history. In instances where the event camera observes minimal motion, generating a sparse number of events, the frame buffer ensures the preservation of the 3D human body pose even when no events attributed to human movements are captured. The head-mounted device generates a considerable number of background events compared to those originating from the human body due to the high mobility of the head. To address this challenge and mitigate spurious estimates due to background noise, we utilize a segmentation decoder to generate human body masks. Confidence maps are then created for events attributed to the human body using the human body mask. By multiplying the confidence map with the event history, we obtain human-weighted event history. The human-weighted event history is added to the current LNES frame, emphasizing human-related events while suppressing background noise, which serves as the input to our network. We compare our method to a variant of event hands. In this experiment, we observe that our EventEgo3D produces accurate estimates despite the numerous background events. Event Hands was originally designed for 3D hand tracking from an external monocular event camera, and we adapt this approach for our setting. We also compare our method to a variant of Mo2Cap2, a real-time method for 3D reconstruction of the human pose from monocular egocentric RGB views. EventEgo3D substantially outperforms Mo2Cap2 in our experiments. We perform an ablation study to validate the components of our architecture. Here, we observe that the incorporation of the residual event propagation module enables reliable predictions when dealing with background clutter in the event stream. Addition of the segmentation branch to the baseline improves the overall mean per joint position error. However, the lack of precise correspondences between the human body mask and event streams results in inaccurate 3D poses. The absence of the confidence map in the residual event propagation module produces inconsistent 3D poses, which is also reflected in a higher mean per joint position error. Here, we find that the events generated by the human body hold more significance in the input frame, whereas in the LNES frame, higher weights are assigned to recently fired events. We show additional results with reference third-person RGB views. We develop a real-time demo to estimate 3D poses of head-mounted device users using our approach. The entire computation takes place on a laptop in the backpack carried by the user. The estimated 3D poses are transmitted to another laptop through the network for visualization purposes. Our method accurately predicts the 3D poses of the subject in real-world scenarios, even during complex actions such as sitting in a chair, where the knees and feet can be hidden. Note that the transmission of data through network sockets causes a slight lag in the visualizations. Taking advantage of the high temporal resolution and high dynamic range of event cameras, our EventEgo3D method accurately estimates the 3D poses even when the wearer engages in fast motions, such as practicing martial arts, and under low-light conditions enabling egocentric 3D human motion capture in dark environments. In scenarios when the user remains still and only a few events are incoming, our method preserves its 3D reconstruction accuracy. See the paper for further details. To conclude, the proposed method in combination with the head-mounted device demonstrates stable regression of the subject's 3D poses, even when there are sudden motion pattern changes. Thank you for watching. The code and the dataset are available on the project website.